In this video, we're going to look at vectors in 3 dimensions. So before we look at vectors in 3 dimensions, we're going to take a minute and just look at graphing in 3 dimensions. So we have a lot of practice at graphing in 2 dimensions on the XY axis. So we can see here we've got our XY axis. So picture the graph paper that you're used to, and you're just going to set it on the table. All right, and you got your X, we'll say this is the positive X axis and the positive Y, and now we're going to create a Z axis, which is coming up and down. So now we can describe a location in 3 dimensions relative to the origin. All right, so we could say it's 2 units in the X direction, 3 units in the Y, and then maybe 3 units under the table. So we go down, and we're going to look at another picture of that here. So in this scenario where we've got the positive x coming towards us and the positive y, we call this the right-hand coordinate system. And we're going to look at GeoGebra, which sometimes the coordinate system gets turned around and you got to figure out where you're at. So when we're looking at 3-dimensional graphing, we don't have quadrants anymore, right? In 2 dimensions, we have 4 quadrants. In 3 dimensions, we have 8 octants. And those are the 8 3-dimensional spaces separated by the planes created by the axis. So we're used to all of our graphing basically done just on this light blue plane right here. This on the XY plane. That's all the graphing we've done. Now we're going to extend it to 3 dimensions. Okay, so we have an XZ plane, which would be the intersection of the X and Z axis. And we have the YZ plane, which is this green one. That's the intersection of the YZ plane. Sometimes it helps just think of this like a room, right? Like the corner of the room. And maybe X is this direction, Y is that direction, and Z would be up. And that would be in your first octant where X and Y and Z are all positive. So if we want to graph a point in 3 dimensions, we're going to start at the origin. And that point is 0, 0, 0. Now in this picture, we're going to assume that A, B, and C are positive numbers. Right, so A is positive x coming towards us. If it was negative x, we'd be moving back. Our B is our y value. If it's positive, we're going to move to the right. If it's negative, we're going to move to the left. Our C value is our z value. If it's positive, we're going to move up. And if it's negative, we're going to move down. So for example, let's say we wanted to graph the point 3, 4, 5. So we're going to start at the origin. We're going to come 3 units out, 4 units to the right, and 5 units up. And that's going to be the location in space. Putting a box, a little 3-dimensional box here, can help you visualize that space from 0, 0, 0 to 3, 4, 5. Let's look at another point. Let's say we want to plot -2, -3, +5. So starting at the origin, since the x value is -2, we're going to go away from us 2 units. Y is -3, so we're going to go left 3, and then Z is +5, so we're going to go up 5. And this would be in a different octant, right? Okay, so like we have lines in 2 dimensions, we have equations of planes in 3 dimensions. So let's go back to our 2-dimensional world for just a second. And let's say we have our good old XY axis back in the 2-dimensional world. And we could have the equation of a line in 2 dimensions. Say we have a vertical line like this, that's 2 units here. So the equation of this line is x equals -2. And if I have a line over here at 2, and I do a vertical line, then the equation of this line is x equals 2. Well, in 3 dimensions, let's look at this picture down here. If I talk about the equation x equals 2 in 3 dimensions, this is the line x equals 2 laying in the xy plane. Okay, picture taking this guy right here and laying it down flat. Okay, here's your I'm going to put arrows on the positive x and the positive y. So the positive x is here and the positive y is here. So there's your line right there, x equals 2. But if I'm graphing in 3 dimensions and I talk about the equation x equals 2, then I don't have a line anymore, I have a plane. All right, so if we're going to graph x equals 2, basically we're saying, all right, the plane x equals 2, or the equation, the graph of x equals 2, x has to be 2. Y can be anything you want, z can be anything you want. Alright, so if I think about graphing all those points, I got to come out to, then y can be whatever I want. So I can go left or right, whatever I want. And z can be anything, so I can go up or down. Now for the sake of clarity in this picture, we're just seeing what's in the, I'll call it the first octant. And when I say that out loud, I'm not sure the actual numbering system, you know, like quadrants is 1, 2, 3, 4. There's probably an official numbering system. I would bet $1,000 that the octant where x, y, and z are positive is the first octant. So I'm very comfortable with that. We'll call that the first octant here. So this light blue square is the piece of the plane x equal 2 that lives in the first octant. But that plane actually would go to the other octants, right? It would go this way, it would go down, and it would color all in like that. I don't want to mess up my picture too much. Alright, so similarly, if I have the line y equals 4, then that means that line is not a line anymore in 3 dimensions, it's a plane. The y value has to be 4. You can make x whatever you want, and z whatever you want. Alright, so x, I can come out as far as I want, y has to go 4, and z is going to be up or down. So you could pick whatever number you want for x and whatever number you want for z, and if y is 4, you're going to be lying somewhere on this plane right here. So this plane is perpendicular to the xy axis, or the xy plane, I should say, the xy plane. And similarly, if I have the plane z equals 3, I think this is almost the easiest one to visualize. X can be anything, y can be anything, but z has to be 3. So for me, I just visualize like anything on the 3rd floor. If 0 is the 1st floor of a building, you know, z equals 1 is the 2nd floor. Z equals -2 would be, you know, down 2 levels in the parking garage or something. Z equals 3 would be anything on the plane that represents the 3rd floor of a building, say. Alright, so here's just another picture of the plane y equals -3, and it's passing through this point 2, -3, 7. Alright, let's plot that out. 2, come out this way. X is 2, y is -3, z is 7. That gets us to this point up here. And this plane here is parallel to the xz plane. So the xz plane is the plane that goes through these two axes. Well, we can take everything we know in 2 dimensions and extend it to 3 dimensions, right? We could talk about the distance formula. We're used to the distance formula in 2 dimensions, basically looking something like this. All right, so here's the distance from P to R. Now this is graphed in 3 dimensions here, but in this diagram, the point P and the point R have 2 different x values, x1, x2, 2 different y values, y1, y2, but the same z value. So they're on the same floor, they're on the same level up. So if I want to find the distance from P to R, I'm just going to use the Pythagorean theorem in this plane, z1, and I could get this distance here for PR. But now I want to extend that to 3 dimensions, alright? So now I'm going to go up here, and I really want to find what's the formula for P to Q, where those aren't lying on the same z-plane. All the coordinates could be different, right? x1, y1, z1, x2, y2, z2. Well, now I have to throw in this dimension here, the distance from Q to R. Notice for these points, they only differ by their z-coordinate. So the distance from Q to R is going to be whatever z2 is minus z1. So now I get another right triangle. This is a right triangle right here. This is a right angle. Alright, so I can do this guy squared plus this guy squared. All that under a square root, and it's going to come out to be that, which you can see is just an extension of the 2-dimensional distance formula. This part's the 2-dimensional distance formula right here. Right, so now if I'm in 3 dimensions, I'm just going to throw in this piece. And actually, you could think, hey, I've been using the 3-dimensional distance formula the whole time. It's just that these were both 0 because I was in the xy plane. So here's our official definition for the distance between 2 points, or our formula in 3 dimensions. And we could also talk about the midpoint formula. The midpoint formula in 2 dimensions would look like this. It's the average of the x values and the average of the y values. Well, now if I want to go to 3 dimensions, I have to average the z values as well. Right? If the point Q is on a certain floor up and the point P is on a certain floor up, I need to find the halfway point between there, and that would give me the midpoint of the z coordinate. I just throw that into my midpoint of the other x and y coordinates. So with that set up, let's talk about vectors in 3 dimensions. So we've done vectors in 2 dimensions, and we know they have 2 components. And those components represent a horizontal distance. Say I have the vector 3, 2. All right, so that represents a vector which could be in standard position, but really the tail could be anywhere. And I'm going to move 3 units in the horizontal direction and 2 units in the vertical direction, and that would be my vector. So just for clarity, right, I could start wherever I want. I could start here. That could be my tail of my vector, and as long as I move 3 units to the right and 2 units up and create this vector, that's the vector 3, 2 as well. It's just not in standard position. These 2 vectors are equivalent because they have the same direction and the same magnitude. So for a vector in 3 dimensions, and for those of you guys that might have the worksheet, the notes that go with this, we're starting the first example here. Let's say I've got the vector 5, -12, 2. So now this is in 3 dimensions. All I'm doing is adding another component here. So we're going to look at the magnitude of this and some other things. We're going to add vectors in 3 dimensions and all the stuff we did in 2 dimensions. But before we do one of those, I want to show you kind of a cool way to work with these and visualize these. A lot of you guys know about Desmos. There's a website called GeoGebra. Here's the spelling here. And if you just go to GeoGebraorg, you'll get this particular page. And I'm going to go to the 3D calculator. 3D calculator right here. Alright, so what we can do here is we can graph points or vectors in 3 dimensions. So the vector we have is has a head at, what did we say, 5, -12, and 2. Okay, so I'm going to plot the point at 5, -12, 2. I need to put a equal sign in here. Put the point equals. A lot of learning how to do with these is just do the correct notation they want. So here, when I'm using GeoGebra, sometimes I get confused about what is the x and y axis. So I'm going to go to the settings up here, and let's go to settings here, x-axis, label, x, y-axis, label, y, z, no, y-axis, label, y, and z-axis, label, z. Close that. Okay, now I can see what's happening. Alright, so this red one is the x-axis, and if you click home, that takes you to how they like to have it oriented, which is a little different than what I was showing you before. See, they've got the positive x here, negative x there, then they've got the positive y moving away from you. I don't know, I just think it's a little weird. So if we want to change it to how we had it, you just grab it and flip it around. Okay, so now I have the x, positive y, positive z. That's how we were doing it. Now I'm going to use my mouse and scroll out. See, I was like this, I couldn't see my point, so I'm going to scroll out. Now I can see this point, 5, -12, 2. See, I'm going to grab this so you can see it like that. Okay, so it's coming out 5 units towards us, -12 to the left, and then up 5. Right, so that's kind of cool. You can get a visual for what's happening. So now if I want to look at this vector, let's see if I can remember this. I'm going to go vector, parenthesis, p, enter. And it named it u. It's naming this vector u. It's putting it in standard position. So now we have the vector with the initial point at the origin and the terminal point here. So the next question is, what's the magnitude of that vector? Well, we just did the distance formula, right? And the magnitude is the distance between these 2 points. So let's go back over here and let's find the magnitude of vector v. So since this guy is in standard position, since our initial point, or the tail of our vector, is at 0, 0, 0, and I like to call it the terminal point, sometimes called the head of the vector, is at 5, negative 12, 2. Basically what we're going to end up doing is 5 minus 0, negative 12 minus 0, 2 minus 0, right? So if it's in this kind of component form, then when you're doing the magnitude, it's just a matter of squaring each of the components and taking the square root of it. Alright, so the notation for magnitude still with the 2 bars kind of look like an absolute value. So we've got 5 squared plus negative 12 squared plus 2 squared. And we can all do this arithmetic. 25 plus 144 plus 4, what does that give us? 169 plus 4, 173. Alright, so the magnitude of that vector is 173 square root of that. Now we might ask, what's the direction of that vector? And that's going to be a little more complicated in 3 dimensions. And we're going to learn, not in this video, but in the chapter that we're in, and probably if you're watching this, the chapter you're in, how to find some angles in these 3 dimensions. So our official definition of magnitude of a vector is very similar to the distance formula between the points. Here we're just showing it in vector notation, with the vector PQ having these components, all right? And then the magnitude is simply the distance formula. Well, just like in 2 dimensions, we have unit vectors in 3 dimensions. And when we were in 2 dimensions, we talked about the vector I, which is the unit vector in the x direction, and the vector j, which is the unit vector in the y direction. And now we're just going to extend that to 3 dimensions. So in 2 dimensions, the vector I, we just said, was 1, 0 in 2 dimensions. But now in 3 dimensions, the z value would be 0, right? In 2 dimensions, the vector j is 0, 1. So in 3 dimensions, it has a z component of 0 as well. And we can see these pictures down here. Well, now we need a unit vector in the z direction, and that vector is going to be called vector k, and it will have components 0, 0, 1. So every vector can be expressed as the sum of these 3 vectors, including scalar multiples. Okay, a sum plus scalar multiples. So let's go back and look at this picture real quick, and we might think about, how could I express this vector using vectors I, j, and k? Well, if I'm going to go 5 units in the x direction, that's 5 I vectors, right? I need 5 I vectors to get out here 5 units. And then I'm going to need to subtract 12 j vectors to move to the left, and then I'm going to have to add subtract k, no, I said that right, j, subtract j vectors, those are our y units, sorry about that. Okay, so let's say that one more time. I'm going to have to add 5 I vectors, subtract 12 j vectors, and then add 2 k vectors to get up to there. Alright, so let's just write that out so we can see what that looks like and show that that's true. So the vector I is 1, 0, 0. It's good practice. It's a little bit trivial, but it's good practice to work with the vector addition and scalar multiplication. So here I'm multiplying these vectors by a scalar, my unit vectors. Remember, a unit vector is just a vector with magnitude 1. I mean, this can get a little tedious here, but that's okay. So we're going to subtract this vector, which will move us in the y direction to the left 12. And then if I add on this vector, that's a vector 2 with a magnitude of 2 just pointed straight up, right? So if I add these together, I add all the x components. 5 minus 0 plus 0 is 5. 0 minus negative 12. I got a minus there. I should have put a plus there since I distributed my negative into my components. So negative 12, and then 0 plus 2 is 2. We end up with the vector v. Now, if I want to find the unit vector in the direction of vector v, so that means it's headed in the exact same direction, but it only has a magnitude of 1. We figured out that our vector v in a previous slide over here, we figured out our vector v had magnitude square root 173. So if I want some vector u, we'll say that's a unit vector, if I want that vector to have magnitude 1, then what I'm going to have to do is divide every component of v by the square root of 173. And by keeping these components the same, I'm keeping the vectors parallel to each other. Let me write this a different way to really bring that home. Let's say I write this as the scalar 1 over the square root of 173 times the vector 5, negative 12, 2. Right, so what I'm doing here is I'm taking 1 divided by the magnitude of vector v, and I'm multiplying that by vector v. So any vector that is vector v times by some scalar is going to give you a vector parallel to v. Remember, this isn't a vector. This is, you really got to get used to this notation. You see this vector v sign here and you're like, oh, that's a vector. It's not a vector because it's got the magnitude symbol. It's actually a scalar. It's a real number that represents the length of that vector. So if we take a scalar times that, we're still parallel. So this is our unit. This is our unit vector that's in the same direction as v. And I'm not going to take the time right here in this video. But if you wanted to prove to yourself that this was a unit vector, go ahead and find the magnitude of vector u. And find the magnitude of vector u. Take the square root of this squared, each component squared, right? X component squared, Y component squared, Z component squared. That better come out to be 1. Be a good idea to prove that to yourself. Alright, the last thing we want to do is look at an application in 3 dimensions, and I think I will do that in a separate video.